All right, when you picture an EV, what comes to mind? Probably a giant battery, right? Or maybe that silent, powerful motor. But there's this unsung hero, this brain that makes the whole thing work. And that's what we're digging into today, the electric vehicle controller.
You know, one of the coolest things happening in the EV space right now isn't even about brand new cars rolling off the assembly line. It's about this incredible art of conversion, taking old classic gas guzzlers and giving them a totally new electric life. I mean, as this quote points out, it's this fantastic way to recycle, cut down on pollution, and basically turn automotive history into a vision for a sustainable future.
And this isn't some niche garage hobby thing anymore. We're talking about seriously high-profile, absolutely stunning conversions of some of the most iconic cars ever made. Think about it. A beastly 1968 Mustang, a classic Porsche 911, even the beloved VW Bug, they're all getting these high-tech electric heart transplants. It just goes to show, pretty much any car can be brought into the electric age.
But that leads to the million-dollar question, right? It's not as easy as just yanking out an engine and dropping in a motor. How do you get a super powerful high-voltage battery and a complex high-tech motor to actually talk to each other, to speak the same language? And more importantly, how do you translate the simple act of you pressing the accelerator into that smooth, instant, controlled power that EVs are known for?
Well, this gets us to the heart of the technical challenge, what we'll call the uncontrolled problem. And yeah, you really can't just hotwire an EV and hope for the best. The best way to think about it is this. Connecting one of these massive battery packs directly to an electric motor, well, it's like trying to take a sip of water from a fire hose. You've just got this raw, massive, completely unregulated blast of power. It's total chaos, it's dangerous, and it's wildly inefficient. So let's break that down. Without a controller, you get a mess. The voltage is all over the place, which actually reduces the battery's power output, and the car's performance is just terrible. But add a controller into the mix, and everything changes. You get stable, regulated power. You get proper power delivery. And that means you get the optimal performance and that awesome instant torque the second you touch the pedal. Okay, so how do we tame that fire hose of power? Well, it's time to meet the brain of the operation, the EV's electronic command center.
Right at the heart of it all is the vehicle controller itself. This thing is the central processor. It literally reads the signal from your foot on the accelerator, analyzes it in a split second, and then commands the motor. It tells it exactly what to do, how fast to spin, how much torque to apply, and whether to go forward or reverse. It is the #1 decision maker. Now, the controller isn't a solo act. Think about it. The main battery pack is pushing out hundreds of volts that would instantly fry your headlights, your stereo, your windshield wipers, all the normal car stuff. That's where the DC-DC converter steps in. It's basically a step-down transformer. It takes all that high voltage and safely knocks it down to a familiar 12 volts to power all your accessories. And rounding out our team of electronic wizards is the battery management system, or BMS. You can think of the BMS as the personal bodyguard for the most expensive part of the whole car, the battery pack. It is constantly monitoring everything, the health of the cells, the temperature, the state of charge, all to make sure the battery is safe and that it lasts for as long as it possibly can. Okay, so we've met the team. We've got the controller, the converter, and the BMS. Now let's zoom in on the controller's main gig, translating what your foot does into actual forward motion. This whole process happens in the blink of an eye, but let's walk through it. First, you press the accelerator. Simple enough. Second, the controller gets that electronic signal. And here comes the magic part, power regulation. The controller uses this really clever technique called pulse width modulation. Now, the easiest way to picture this is to think of a light switch being flicked on and off thousands of times per second. That's what the controller is doing with the power from the battery. This super precise pulsing means the motor gets the exact amount of power it needs for what you're asking it to do. And that is the secret behind that buttery smooth, instantly responsive acceleration that everybody loves about EVs. So you can see the controller's to-do list is way longer than just make the car go. This thing is an absolute master of multitasking. In any given millisecond, it's managing the drive torque, it's optimizing regenerative braking to put power back into the battery, it's overseeing the car's entire energy use, running constant system checks. Oh, and it's also responsible for displaying all that info on your dashboard. It is juggling all of that all at the same time.
Now, a good controller isn't just a powerful processor, it has to be a great communicator too. And here's the catch. Not all electric motors speak the same language. So the controller's strategy, its whole approach, has to be perfectly tailored to the specific type of motor it's working with.
Let's look at two of the most common types. You've got your induction motors. These are the workhorses. They're simple, they're tough, they're relatively cheap. That's why you find them in a ton of mass-market EVs. Then you have brushless DC motors, or BLDC. These are famous for being super efficient and really quiet, which makes them a huge favorite for those custom EV conversions we were talking about. And each one of these motor types needs a completely different set of instructions from the controller to get the best performance out of it.
And to squeeze every last drop of performance out of these motors, controllers use some pretty complicated strategies. One of the big ones is called field-oriented control, or FOC. Now, without getting too deep in the weeds, what this lets the controller do is achieve maximum possible torque even when the motor is at 0 RPM, a complete standstill. That is the secret sauce behind that insane pin-you-to-your-seat acceleration you feel in an EV. And on top of being fun, it also makes the whole system way more efficient, which means you get more range.
All right, so we've seen how these controllers are the essential piece of the puzzle, the thing that tames the power and makes an EV work. But what does all this mean for the future, especially for these custom-converted electric cars? Let's take a look at the road ahead.
Of course, it's not all sunshine and roses. We have to be realistic here. There are some big challenges. For one, the initial cost of a quality conversion can be pretty high. You're often dealing with a more limited driving range than a factory EV. And then there are the big ones: added weight, space constraints, and navigating all the safety and regulatory standards. Oh, and yeah, you're probably going to avoid any warranty the car had.
But even with all those hurdles, the technology is just moving at a breakneck speed, which kind of leaves us with this final big question to chew on. As these controllers, these electric brains, get smarter and smarter, more efficient, more integrated, what does that mean for the future of transportation? What will personalized, sustainable travel really look like when we can truly teach any old car some brilliant new tricks?